That block's been in the water, and that is at it's pretty much 97 degrees again. There we go, 97. So we just need to do the experiment, see what it goes up to, and then weep tears of joy at how awesome physics is. All right, so we'll make the transfer. There it is. Pop that in there. Graph. Discard. And then slosh this around. Now the aluminum specific heat was much closer to that of water for the first one, so the final temperature of roughly 33 degrees Celsius, I would expect the temperature for the iron to be let's see, what would I expect with the iron? Iron's going to lose it more readily, but there's a lot more mass. That we'll find out. Looks like that's sort of hit a steady state there. Temperature of the two probes is about the same right now. Yeah, that seems to have done its bit. All right, so analyze, statistics, Boole temperature. We have a max of 38 degrees. That seems to be the final temperature. So the math problem, well, pretty much it's 94.2 times 4.186 times, well, 17 equals negative 248.78 times C times, doing the fancy math here, is that 59? Negative 59? So what do we get on the left-hand side?
6,703.4604.
That's going to be equal to, and then this times that. The negatives will annihilate each other. $14,678
.02.
times the specific heat.
.4567
Units?
degrees Celsius. No.
Joules over gram Celsius.
Emily?
Joules over gram Celsius.
Degrees Celsius. Joules per gram degree Celsius. We got 0.4567 with this simple experiment. The accepted value is 0.450. Woo! I hope I can carry the luck that I have with this class into the next one.
Could this bring our grade up?
Again, does come across as flippant, but these points matter if you're anywhere close to the border. I should turn this off.
Probably.
And eventually deal with it. All right, questions?
The units to begin with were like, if you give, like if you say, if you gave your mass in kilograms, you would have to change it to grams.
It really depends upon the units for the specific heat. If this units for a specific heat is something per gram, then
Okay,
you
right.
need to get it into grams.
Okay.
Or convert that into kilograms, one or the other.
Okay.
Probably easier to convert the mass to grams without making a mistake than the other one.
And the thing with the joules, you're always gonna give that, right?
Or give you enough information to find it.
To find out. So there could be calories.
It could be, but 1 calorie is 4.186. Yeah, 6 joules. Although I do see that this number, I see that number vary depending upon the source, but it's something around there. All right, let's take a break, stretch legs. We'll come back, talk about melting things.
I'm so excited to get back in here.
Physics will pump us all on.
That will kill us.
Yes, one of those two. Maybe it'll pump us up to the point where we burst. All right, so we have dealt with putting energy into a system, the temperature changes, all that's well and good, but we know for a fact, I'm assuming all of you have experienced melted ice. We know that you put energy into some systems and they will change what they look like. So let's deal with that. So first off, just dealing with the 3 main phases of matter. Got liquid, solid, and gas. Besides those 3, what is another phase in which matter can appear?
Isn't it like plasma?
Yep, plasma is one of them. And the connection with plasma phase and plasma blood is that the person who came up with the name for the phase, when he was looking under a microscope at what was plasma, he thought it looked like blood plasma. So we called it the same thing. So anyway, if we go from a solid to liquid phase, what is that called?
Melting.
Yep. We go from liquid to solid.
Is freezing.
Yes.
Make sure I was looking at the right arrow that you drew.
If we go from liquid to gas,
Evaporation.
and I'm going to put parenthetically boiling here, there is a distinction between the two. And then gas to liquid.
I have to go, I'm sorry.
Something like condensation.
I'm sorry if this was too controversial for you.
No, I'm sorry.
Could be condensation.
Yep. Or since I'm doing gerunds here, condensing.
Oh, condensation.
And then solid to gas,
Convection, something like that.
not convection. Think back to the last time there was no, basically the 2 times that I see it are if you've got a block of blanking on the name of it, the ice, the big
Dry
ice.
ice.
Dry ice. If you have a block of dry ice, that's basically frozen carbon dioxide that evaporates. It goes pretty much from solid to gas form. Snow does it also. That's the other time that you see it. Yeah, some of the snow melts, but some of the snow will go from solid to gas phase. Guessing people are drawing a blank here.
I remember hearing this name. So,
Sublimating. There's a video that I saw on the internet, someone trying to, who was convinced that snow was not really snow, it was some dangerous chemical. And he took a blowtorch to snow and said, see, there's not much liquid water there. And someone chimed in, you know, with the respect that you expect on the internet, and said, that's actually called sublimating. And then a few choice words after that. And then gas to solid. It's what you do before the trial. Deposition. Or, I guess, depositioning or depositing. I'll go with depositioning. Although depositing might be the word. All right, so first off, evaporation versus boiling. The difference is temperature. Boiling is you're going from liquid to gas because of temperature that's been put into it. You deliberately putting heat into it to raise the temperature and it boils. Evaporating can happen at room temperature. So you just get one molecule that's going the right speed to escape, and boom, it's off into the atmosphere. Now, for each of these phases, when you are going from one phase to another, you actually do not change temperature for that particular, for those molecules. What they're doing is, if you're in the solid phase and going to melting, you're basically separating them and to put them into the liquid phase, and then gas, you separate them even more. So what's happening here is a change in the potential energy because the position of the molecules is changing. It's not, they're not getting more excited, they're just moving apart. Now, it takes a certain amount of energy. There's no temperature change, so it's not MC delta T. It's simpler than that. So for the transitions of phases, the Q is just MC. Now, there's two different C's of importance here. This would be C sub F, and over here, MC sub V. This is the latent heat of fusion. When things are fused, they stick together, so it's still latent heat of fusion, whichever way it's going. And over here, vaporization. So for example, see, I've got it for water. The latent, seems like I had a decent black marker at one point. There we go. The latent heat of vaporization for water, CD, is equal to 597.3 calories per gram, or 2,500,000 joules per kilogram, or 2,500 joules per gram. So whichever you happen to be working in. the latent heat of fusion for water, and it probably would make more sense if I put CV over there and CF over here, but I didn't, is 79.7 calories per gram, or 330,000 joules per kilogram, or 330 joules per gram. I'm not expecting you to memorize those, but we'll be using these in just a moment. So if I had 50 grams of ice and I wanted to figure out how much energy does it take to melt it, we can do that now. So if I had 50 grams of ice at, we'll just say, negative 10 degrees Celsius, energy to melt it, that's what we're trying to find. First thing we need to do is we need to take that ice and get it up to the melting point. And what's the melting point? What temperature?
0 degrees Celsius?
Yes, it is. That's why 0 was established there. All right, so, well, to change the temperature, I'm putting in heat, so MC delta T. This is to get the ice from negative 10 degrees Celsius to 0 degrees Celsius, the melting point. M, 50 grams. Specific heat of ice, or specific heat capacity of ice, if you want to go throw in the extra word. 2.05 joules per gram degree Celsius. 2.05 joules per gram degrees Celsius, and because that's the number I saw, it looks like we'll be working in joules. Times the change in temperature, which would be,
Minus 10.
say it again?
Minus 10.
So it starts at negative 10 and then changes negative 10?
Final, like, 1 second. Final.
Final minus initial. You're subtracting negative 10. I'm not quite sure what that, how to interpret that look. It's, the change is 10, not negative 10.
Oh,
Positive 10.
okay, got it.
So the energy it takes in order to get ice to the melting point, well, 50 times 2.05 times 10, which is units.
Joules.
All right. That's the amount of joules it takes in order to get ice up to the melting point. Now we have to melt it. So we're putting energy into the system, so whatever the heat is to melt it is a positive number because we're putting energy in. And so to melt it, we do Q is equal to MCF. And it is up there. See, I have joules and grams, so let's do that last one, 330. So this is 50 grams times 330 joules per gram. This is right. Joules. So it takes a whole lot more energy to melt it than it does to change the temperature. So the total amount of energy is just the sum of those two. Doing the fancy math here, we got 17525 joules. That last this thing there is a J. So 17, a little over 17,500 joules in order to melt that 50 grams of ice. And 50 grams of ice, that would be 50 grams of water. So 50 grams of water would be basically to there. And then ice expands a little bit. So it would basically be a piece of ice that the size of the cylinder, then that roughly that tall. Questions to there? All right. Now, so we still have this 50 grams of ice here. Now I want to boil it. So what do I do next? I have 50 grams of, I've melted it already. So I have 50 grams at 0 degrees Celsius. It's in liquid form. How much energy does it take to boil it? Or what steps would you take? Not looking for an actual answer yet.
You would need to figure out what temperature it boils at.
Okay. What temperature does water boil? Assume standard atmospheric pressure.
100?
All right, 100 degrees Celsius. So first we have to get it up to 100 degrees Celsius, and then we boil it. All right, so let's see. We had negative 10 degrees Celsius to 0 degrees Celsius. That was, I had it up there, 1025 joules. Then we had 0 degrees Celsius solid to 0 degrees Celsius liquid. And that was 16,500 joules. And now we're gonna take our liquid, so this is ice, this is liquid water, or what most people call water. 0 degrees Celsius in liquid form up to 100 degrees Celsius in liquid form. And then 100 degrees Celsius in liquid form to 100 degrees Celsius.